that looked at the effect of the Gulf Stream on the mean temperature in Europe. And what they did for this study was they removed the ocean heat transport from a model. They coupled an atmosphere to a slab ocean. And then they looked at what happened to the mean temperature in Europe. And they found that it didn't change too much. And they argued it was because, for the most part, over the course of a season, the ocean stores up heat, and in winter that heat gets released through fluxes to the atmosphere, and then the atmospheric advection blows that maritime climate basically over Western Europe, and that's what keeps Europe. So we all know after this, Richard went on to do plenty more. One of the other side effects of this talk, of this paper, was it inspired a woman named Kathy Kelly at the University of Washington to look into greater detail about what the Gulf Stream is doing to mid-latitude storms. And long story short, my PhD research was basically created by this paper. When I went to wrap up my dissertation, I was going to give a talk on the third part of my research, and I went to lay it out, and I looked at all the research that had gone on over the last 2 years, and there was a lot basically talking about the effect of the Gulf Stream on the mean state of storms. And so I got up there and I said, okay, I'm going to give you 2 take-home messages for the talk. One is that the presence of the Gulf Stream is important for the forcing of the mean state of storm tracks. And the other is that the Gulf Stream forcing variability in the storm tracks, it does not create any signal that I can find in the ERA40 analysis. So basically null result on forcing due to variability. But the first part, I mailed it in because it felt just so obvious to me. And the talk ended up with a result that everybody was really clear on this point, but not necessarily in agreement on the first point. And a lot of it was because Richard Seeger's second author, David Battisti, was one of the main people who still just wasn't convinced about this. So what I wanted to do today was revisit the first point. And for the most part, I'm going to be showing just a review of some really recent literature. And then I'm going to add in an argument that I've created that might be just so simple that it's not worth writing up, and you all can help me determine that. I felt nervous making this talk because it's not relying on a lot of analysis or a lot of rigorous, interesting statistics, which is what I usually give talks as. But I hope you all will forgive me in here, or maybe this is the right setting for this type of talk. Okay, to start out with just a background on mid-latitude storms and storm tracks. So the mid-latitude storms we think of as the weather that we get in winter in New York. And this is the analysis this morning of the storm that we're experiencing. And typically with mid-latitude storms, we think of them having a cold front and a warm front and a huge precipitating cloud mass associated with the storm. Now, when we talk about storm tracks in climate, what we're actually talking about is a statistical measure of the variability of baroclinic waves. And the way they go about getting this is they take an atmospheric field like temperature or geopotential height, and they filter it in time so they can isolate the variability associated with storms. So you cut off all variability less than 2 days, all variability greater than 8 days. What remains is quote unquote synoptic variability, and then you look at something like the variance of this. Usually you'll hear things mentioned like band pass filtered, and that's just what I described. It turns out that you don't necessarily need a complex filter. A 24-hour difference basically acts in a similar method as a bandpass filter. The daily average gets you out of the short range, the diurnal, and then the 24-hour essentially calculates the same thing as a 6-day bandpass. What I'm going to be looking at specifically is what I'm calling V prime T prime bar. I bandpass filter the temperature and the meridional wind speed, multiply them together, and then take a mean. So you might want to ask right away, can we think of these storm tracks as being the same things as a composite of mid-latitude storms? And the answer for the most part is yes. So a study came out in 2002 looking at the northern hemisphere and another one in 2005 looking at the southern hemisphere. And what they do in that study is they grab individual storms and they make composite maps of things such as the maximum wind speed in the storms or the maximum strength of the storms, and they look at density plots of this. And what you see is a pretty good alignment between the maximum in the climatological storm tracks and the maximum in the composites of individual cyclones. I think this is an important point when I move forward, because I'm going to be talking about physical mechanisms related to individual storms. Why do they matter? I think beyond just the weather aspect, when we think about storm tracks on climate levels, the key things are the poleward advection of heat and moisture, and then also momentum transport. And basically, the westerly winds that we see in high latitudes are maintained by a downward transport of momentum associated with these mid-latitude storms. Okay, so just a broad brush picture of what storms look like. For these slides, just the next two, I split and I've given us winter time in both hemispheres. So in the top, we're looking at the eddy, the V prime T prime bar for northern hemisphere winter, and the bottom is southern hemisphere winter. And you see that things accumulate into storm track maxima North Atlantic, Pacific, and in the Indian Southern Ocean. If instead of looking at 850 poleward heat transport, I look at geopotential height at, say, 300, we see a very similar picture as far as where the maxima are. So we can actually break right now.
Thank you.
Thank you.
Thank you.
Very similar pattern, and it's true whether we're looking at poleward heat transport or geopotential height variability. Now, to turn to storm dynamics, to kind of motivate how we can think about things.
So it's interesting, it's Siberia, Russia, all that, they don't have mid-latitude storms, they just have wimpy storms, I mean.
That's right, they have wimpy storms, and that is all mostly related to the Himalayas. Yeah. Yeah. Their storms are important. Actually, the seeding of the storms here might be really important for the midwinter suppression. That's work that just came out last year.
Yes, in the editorial page of all things, right?
What? No, there's a regular journal paper.
But I mean, it was in the New York Times as an editorial column. If you saw that.
Oh, no, I didn't.
Yeah. Very strange.
So if we see a movie with a raging storm in Siberia, we can say it's Hollywood.
But I won't disallow one star, right?
Nothing there.
Okay, so when we're thinking about what initial state sets for the surface for forcing of the storms, one of the things we can think about is what's called the eddy growth rate. And this parameter has the vertical derivative of the zonal wind and then 1 over the stability, the vertical stability. And this was derived originally in relation to the eddy problem, which was actually a barotropic instability, which is just to say, let's not get into details. Let's just leave it at this measurement has been shown to coexist well with the locations of the storm tracks. And some people think of it as a forcing because if you ramp up your low-level meridional temperature gradient, also same thing as the shear and vertical wind, then what you're going to do is strengthen the instability available for a baroclinic wave to form. Now, I just mentioned as a side note that if you go into the papers on mid-latitude storms, what they actually talk about for baroclinic development is a differential in the pressure direction of horizontal advection of temperature. And this is actually what separates the barotropic instability from baroclinic instability. Barotropic instability, you just need this. Barotropic instability, you just need the vertical shear. Baroclinic instability, you start with the vertical shear, but then the differential advection of temperature is actually what's amplifying the wave. And in this sense, in this second sense, the typical picture you get in a class where you're taught about mid-latitude storms is you have an upper level disturbance which aligns with a surface temperature front. The two become phase locked, they say, and you have a growing storm. And the idea here is that it's the upper level advection in the presence of a surface temperature front that is setting up the differential temperature advection. Okay? The other point I want to make in the preview is that the ocean also affects these storms through the surface fluxes. And here I've got a plot of a single storm, and the pink line is showing its progression in time. I've stopped it at a specific time, and I'm showing here just the depression in the 1,000 millibar heights. So we just think of this as the low. This is the equivalent potential temperature, so we think of this as the temperature and the moisture involved in the storm. And you see this nice strong wave of warm, moist air in the front of the storm, cold, dry air behind the storm. And associated with that, you have these fluxes. So if you look at the sensible heat flux, ahead of the storm, you have a flux into the ocean. So this is the storm losing energy to the ocean. And behind the storm, you have a flux of heat out of the ocean. And what this flux is actually doing, you can see it in the sensible and the latent, is it's moistening the air in the Gulf Stream region. And this actually is called preconditioning for the next storm. And the next storm that comes along utilizes that moisture and heat to grow. And there's been a couple of case studies where they go in and they turn these fluxes on and off at different times, and they see that there really is an effect from the surface fluxes from the ocean associated with strengthening the storm through preconditioning or damping the storm later on by removing heat. So I'm showing the picture of the temperature advection again just to motivate a more basic question, which is if these storms are coming along and pushing cold air south and warm air north, they're essentially wiping out the temperature gradient. So why would it be the case that we would have these preferential locations for the storm tracks, given that storms are coming along and wiping out the location where they're being generated? And to answer that question, we're going to go back and just look at a broad scale picture of all the storm tracks. And just a reminder, what I'll show next is this is the meridional temperature gradient at the SST. And what you see is strong meridional temperature gradients show up in basically the same region as our storm tracks. If we put our storm tracks back and overlay it with the strongest SST gradients, we see this strong relationship. Now, Hisashi Nakamura did a study where he took an aquaplanet, and in that way he basically had this southern hemisphere storm track. And he analyzed the strength of the storm track when he had a strong, well-resolved SST gradient and when he had a very weak SST gradient. And he found the storm track gets a lot weaker when he weakens his SST gradient. And he put forth an argument that basically the SST gradient acts to anchor the location of the low-level baroclinicity by preferentially warming more on the warm side of the SST front than on the cold side of the SST front and resetting the low-level temperature gradient. So storm comes in, tries to wipe out the gradient, fluxes from the ocean, reset the gradient. The stronger your gradient, the stronger your storm track gets. This works pretty well down here. Up here we have some issues, and it kind of goes back to the first paper I mentioned where Richard showed that the mountains are really important as far as the mean circulation goes. And related to that, if we look at just the geopotential height field, which we can think of as a proxy for our stream function, so our circulation is following along these lines. What you see in the mean for winter is there's a deflection of the circulation down towards the region where our strong storm tracks are. And in early modeling studies, Manabe and Tony Broccoli showed basically that with mountain deflection, you can get a lot as far as what the storm tracks look like. Now, if we take our stream function and just look at the derivative so that we can get to the zonal wind, these are actually the zonal wind field instead. I contour them on top of the storm tracks, and what you see is, again, a really nice relationship between the location of the strong zonal wind and the storm tracks. And the argument put forth is that on the poleward side of the jet, you've got the cyclonic storms breaking off, and you basically have a maximum always on the poleward side of your jet max. An issue perhaps with this argument is that the stationary waves, the position of the stationary waves, depends on the heating from the ocean. So in a sense, the fluxes out of the Gulf Stream in this region might be playing a very significant role in setting what the strength of the tilt of the stationary waves are. So to get it in more detail, a study came out last year by a student of Brian Hoskins, where they basically took the Hadley AGCM and ran it with a simple configuration for land and very simple SST. So in their simplest runs, they just have SST that cools as we go forward, and then they'll plop down a piece of land. They do one experiment where they just put extratropical land, one experiment where they just put tropical land. And the next experiment I'll discuss, they add in more realistic land. The other thing they add in is orography, so they put the Rockies in. They say in the paper, obviously, the Himalayas will probably matter as well, but for the first order, they're getting at the answer using just this setup. I wanted to point out that because they're just using an SST boundary condition that's fixed, this isn't really going to answer the question about how important the Gulf Stream circulation is, but they get pretty far as far as building blocks for our climate. So here's the case where we just put an extratropical landmass in. The colors in this case are the storm tracks. They look at geopotential height variance at 850. The contours are actually showing anomalies with respect to the mean state where they have no land. And basically when they have no land, things are axisymmetric. And so the contours and the shading match pretty well. This is the zonal wind for this case. And what you see is the zonal jet has this maximum sitting right off of the edge of the land. And we can think of this as the land gets a much stronger temperature gradient than the ocean, sets up through thermal wind balance our strong jet. But if you look at the co-location of the jet and the storm tracks, they're not fitting with what we expect. And further, the storm track is patchy. So they advance it by putting in a more realistic distribution and the Rockies. They go through each one in the paper, so I'm just skipping to the last one here. And you can see in this case, our storm track has this nice southwest to northeast tilt, and it's sitting on the poleward flank of our jet. So that the way that they summarize it in their paper is the tilt in the upper troposphere associated with the Rockies leads to enhanced storm development. And the triangular shape of North America helps pool cold air up in the northeast region so that when the next storm develops, you have a stronger temperature gradient within the storm associated with that cold air pooling. So they're saying, first order, we take our mountains and our land-sea distribution, we can get pretty close as far as storms go, and the distribution of the mean storm track. The next study I'm going to talk about came out around the same time and approached the problem differently. What they did is they took an intermediate GCM, it's Forte. I didn't know the details of it, but I can tell you that it's nowhere near as advanced as had GCM. This we have to think of as having more parameterizations within it. And they look at cases where they have the real land distribution, but no mountains and no ocean circulation, so what we call a slab ocean. And in another case in which we put everything in, and they look at the storm tracks. The shading here is the storm tracks. In this case, it's the eddy kinetic energy that's been bandpass filtered, 250 hectopascals. What you see is, in the case where you just have land, you start to get a zonal asymmetry in your storm track associated with Eurasia being much broader as a continent, when you put in the mountains and you turn on ocean circulation, you get your asymmetry, and you also get a shift in the storm track northward. Then for this one, we'll go through step by step, adding the different pieces. So here again is the figure we saw where we don't have anything added. Now here's the figure where we just add mountains, and what we see, as we expect, is, the contours are the streamlines. So that's the mean circulation. And what we see is that the streamlines get distorted by the mountains, and we start to get a trough, stationary trough, sitting right in the location we want for storm track development. There's asymmetry in the storm track, but it's not strong. When they don't have on the mountains, they just turn on the ocean. Instead, they see less of asymmetry, but a shift in the storm track northward. So the way I think to understand this, and the way they explain in the paper, though, they don't emphasize it, and I'll go into that in a second. So what we're seeing here is this baroclinicity, the ED growth rate that I defined earlier. And then the contours are our stream function. And we're going to build up ED growth rate by adding mountains, and then adding mountains and adding ocean circulation. Okay, so we start out with increased ED growth rate over the oceans. And we can think of this as relating to the mean effect in the colder continental layer over this region, increasing the instability in these regions, thus increasing the growth rate parameter. Now we turn on we add our mountains, we deflect our jet, and we're now blowing the air, the continental layer, right over this part of the ocean, and we increase our instability right in that region. Now they turn on ocean, and instability jumps from being down in this region where that's the Gulf Stream region to being off the coast of Newfoundland. It turns out this is because there's a bias in their model where the Gulf Stream doesn't separate until it gets way up there. And in fact, if you look at the biases in their model, and you accept the idea that the Gulf Stream is setting a low-level baroclinicity that storms are responding to, you can actually see that the biases in their model agree with this type of forcing. So here's their meridional sea surface temperature gradient, and here's the observed sea surface temperature gradient. Their maximum is sitting east of Newfoundland. Here is their storm track, and here is the observed storm track. Their storm track is too far north and too far east.
Well, there's a style ocean. Why isn't it exactly the same intensity as the real world?
No, this is their case with dynamic ocean. Sorry.
With the dynamic.
Yep. Thank you. Yeah. So this analysis, I've gone back and I'm just looking at their full case. The other thing that they do in this paper that I'm trying to understand, or maybe I just disagree with, is they basically theorize that the polar heat transport that the ocean does when they turn on the circulation is the forcing mechanism. You go into their discussion, and later on they talk about the baroclinicity, but their main point is that the ocean heat transport is basically taking the place of the atmospheric heat transport. The atmosphere recognizes this and doesn't do as much transport in that region. It might just be a language thing, but when they say the effect of ocean dynamics is most pronounced in the Atlantic, where the polar heat transport is largest, it makes it feel as if they're really trying to attribute cause and effect just to the ocean heat transport.
Well, the ocean heat transport moves the SST gradient further north, and you just said that the SST gradient is what sets the storm track, and so I don't see that there's any, I don't see there's any problem with that statement whatsoever.
Okay, I'm fine with that interpretation. My interpretation was that they weren't connecting that second physical mechanism here, but I totally agree with you. No, I think you're exactly right.
Well, this sort of goes against all the idea of other papers which show that by turning off the circulation you don't alter the baroclinicity as much as the North Atlantic. So it's not a resolved issue that.
Well, no. What paper says that you don't alter baroclinicity if you change the ocean heat?
Well, I mean, some of the first results that you showed, that's the impression that I got.
Is that what you would say?
So the Seeger paper doesn't take any time to really go into what the storm tracks are doing. But offline, this is a really interesting question because in that paper you look at two models. And one of the models is the GISS model from that time, which they say had dynamic sea ice. And you look at what happens to the change in SST in the GISS model, and it doesn't cool over the North Atlantic the way the other model
Change the
does.
ocean heat transport? That's not true.
Well, yeah, we can look at it later. It's in the Seeger paper, so.
Well, the Seeger paper is very confusing on a number of levels, mainly because everybody thinks they're talking about one thing, but they're being very specific that they're talking about something else, which is the gradient of temperature across Labrador to Europe.
Yeah.
Right? Whereas everybody else has been talking about the temperature in Europe. Right?
No, I agree, and it's also the case that in that model they put some sort of observed Q flux. They have to have some Q flux in their model.
Which is an implied ocean heat transport.
Yep, exactly. So they have that in there, but separate from that, they just have figures of what happens to the SST in the two models. And in one model, the SST cools drastically in the Gulf Stream region, and the other it doesn't. And they attribute this to the model's treatment of sea ice. So it's something that I kind of.
I think that's true.
Yeah. So to summarize what we get from the Brayshaw and Wilson paper, I think we have the orographic deflection of the westerly jet by the mountains, and an orientation of the North American continent, setting up first order the location of our storm track. But the storm track position can be shifted by our Gulf Stream, our western boundary current, because of its influence on the meridional temperature gradient. So with that in mind, I put forth to you an incredibly simple theory. So if we go back to our pictures of the mean state, we have our SST distribution and then our Gulf Stream. And our mean currents in our Gulf Stream basically sit right south of the strongest gradient in SST. If you look in the atmosphere, the wind here is showing the 10-meter circulation. You see this mean wintertime circulation blowing cold continental air over the ocean. And then the shading here is the total sensible plus latent heat flux. And I'm basically returning to this idea about what happens over the course of a season. And I'm showing from November to February the difference in SST. So I just take the climatological November and subtract out the climatological February. And what you see is the maximum cooling occurs right along this region, what we call the slope water, north of the Gulf Stream. And then over summer, radiative heating and also sensible heating related to the continent warms this water back up, and so this whole process can happen again each year. But if you look at the location of the cooling, what you can see is that it's bounded strongly by the Gulf Stream current. And the other thing about the cooling is it's not occurring where the maximum heat flux out of the ocean is. So our maximum heat flux out of the ocean is occurring south of this region of maximum cooling. And we put all three of them together. Contours are now showing the maximum flux out of the ocean. Shading is showing the cooling, and then our ocean currents. We see that the Gulf Stream is a strong enough current that it's injecting heat to replenish the sea surface temperature and basically account for the flux of heat out of the ocean and basically prevent a larger region from cooling. And what we would think a larger region of cooling would do is basically wipe out this meridional temperature gradient. So to try and look at that, I had the luck of Suzanne Dickinson running a mixed layer model and being able to do an experiment for me where she can basically go in and calculate the sea surface temperature offline based on the observed fluxes from the atmosphere as well as the observed horizontal fluxes in the ocean associated with the currents. So you can go in and say at each point, here's what my temperature would be if I turned off the horizontal heat transport. And I just had to run it for one winter, and then I calculate the temperature gradient. And you see, if we keep advection on, we have a gradient that remains very strong. We turn advection off, the gradient gets wiped out. So what I'm thinking here is that the ocean circulation, even in the North Atlantic, is anchoring the mean position of the storm track. Because if you're wiping out the gradient, you're basically allowing baroclinicity to grow, the baroclinic region to grow throughout this region and not have necessarily a maximum. And your storm tracks will basically be able to go, storms will basically be able to form wherever they want through here. And if we go back and think about the Wilson result, this is really consistent with this idea. In their slab ocean experiment, their storm tracks were broad throughout the North Atlantic. And then when they turn on ocean circulation, it tightens up. So just to conclude, from observations here, I've got the ED growth rate from midwinter and late winter. This is mid-December to mid-February. This is mid-February to March. And what you can see is it doesn't change very much, but if anything, it just fixes its maximum over the Gulf Stream region. And kind of related to this, a paper in 2009 that was using a regional atmospheric model went in and said, okay, how does my storm track change when I change the resolution of my SST? I'm going to, what Tim did, Tim Willings, he increased the spatial resolution of his SST, and he looked at the difference in storm tracks and saw they improved. He looked at improving the temporal resolution of his SST boundary condition, updating it more often, and his storm tracks improved. So I feel like it's not, I'm not saying the Gulf Stream is all or nothing, but I'm saying if you actually thought about taking away the circulation associated with the Gulf Stream, we would see a pretty significant effect as far as what the storm tracks look like. And that's it. Thanks.
I think you should do a Hoskins world without the topography, without the Rocky Mountains, and see if you get a storm track that looks more like. See if you can do it without the Rockies.
Yeah. Well, so what's interesting is you go to David Brayshall's website, and he has in the works North Atlantic Storm Tracks Part 2, the role of the ocean. So I should contact him and see if he has a preprint. Maybe that's been done.
Well, I don't know. I think your talk makes perfect sense. It's just the first introduction paper I didn't understand, but maybe that's a different topic. Why do they come up with the conclusion that the storm the Gulf Stream doesn't matter? I still don't understand that.
Okay.
What was that?
The sea.
Do you want to go back to that slide?
They do one where they turn off the ocean heat transport, and they do another one where they lop off the Rockies. And the one where they lop off the Rockies is a better job of maintaining the
And when they turn off the ocean heat transport, they don't get, how different does it look? Like how different does the ocean temperature look?
Yeah, I could show you that. It's still in that.
Remember the days when we didn't have color in PDF?
2002.
My PhD was the first one in our department not to have been cut and pasted.
So here's the difference in January surface temperature in the CCM3 for the model that has ocean heat transport and the model that doesn't. So they find that, yeah, all right, so this region here is shaded and indicates stronger cooling. It shows up better on my PDF. So in that, they're basically finding what I'm talking about, which is that there was a lot of cooling in this region. But that cooling does not impact the mean temperature in Europe. So because of what they were looking for in a result.
It's not true. That's a 3-degree cooling contour that's going through Europe. Why is that non-zero?
That's the temperature, I guess, right?
Yeah. So it's a 3-degree cooling in Europe. How is that not a significant effect?
Well, I guess it's like you said, that they're looking at the gradient between the two.
Right. So it's really very, when you quote this paper, and people quote it very often without making this clear, that their metric for what's happening is the gradient between Labrador and Europe, right? Not the absolute temperature in Europe. And so everybody that quotes this paper and concludes that the Gulf Stream and changes in ocean heat transport don't affect the climate in Europe is a complete misconception. Now, one, quite frankly, which has been encouraged by the authors. But that's a whole other issue.
So this is the difference in the GISS AGCM.
Right.
Why don't you zoom it in?
And again, right, you're right in the middle of the 3 to 6 degrees or so in Europe. I don't see.
Okay, that's fine. But look over the Gulf Stream region. I don't understand why in that case, there's no cooling.
Really, there's no cooling. There's 3 to 6 degrees.
But it's no stronger. There's no gradient in cooling, as we saw in the CCM3.
Well, that could be because was this a slab ocean? I don't know, the resolution might be different, but you probably don't have a very tight Gulf Stream SST gradient in the basic model to start with.
Are both models the same spatial resolution?
No, this is a coarser resolution, but it has better CS.
Better or just more complicated?
But what is your suggestion? From what I understand, your suggestion is a release of the baroclinic zone to the south if you remove the Gulf Stream, for example. So what do you think that means? Does that mean more of a southern track of the storm? Does that mean stronger cold derivation in this model? Does it mean colder Europe in that respect? If it means colder?
Yeah. No, my sense is that it would mean that in the climatology we would see a weaker storm track because the individual storms would no longer form in a preferential region. We would actually see them forming more dispersed throughout the sim. So we would have more storm formation down here and more storm formation up here. And
why would the spreading though mean weaker storms?
Well, weaker climatology
Track.
because when we look at the composite of it. But I also think it would mean weaker individual storms because when we think about the heat that the precondition moistening the low level, that flux being fixed right in this region is really important as far as the next storm coming along being able to tap into that. And we cool this region, now the next storm coming along, it's going to be able to eject warm air from south, but it's not going to have any local source. And additionally, when you watch a storm like the one we're looking at today, that's passing up this way, as it passes up here, it actually fluxes heat into the ocean as well. But that flux is small because it's ameliorated by the warm Gulf Stream temperature. And if we were imagining those temperatures a lot colder, then we would see storms being weakened as they were forming down in this region. So I think, if anything, the Gulf Stream is making our lives worse in New York City in the winter.
Well, the issue of the preconditioning and the latent heat release is something that needs to be really further investigated, especially in models. I mean, how much trust do you have in the model, in the way the models distribute the latent heat in the vertical ones? Even if we say that they get the surface fluxes reasonably well, if they get surface temperature, you get most of the surface components relatively okay, even though their bath formulas are kind of suspect. But even if we accept that they get the release of the surface, okay, how well do they distribute the heating in the vertical, and how much of an effect does that have on the track? So
I'm glad you said that, because that's what my postdoc would tell me is looking at.
I didn't know.
That's good. I got it.
I didn't know it beforehand.
Yeah.
Would it be fair to say that what you are hypothesizing about the importance of the Gulf Stream on baroclinicity is more related to the Gulf Stream leaving the coast where it does, rather than the existence of a western boundary current transporting heat northward? And hypothetically, if the Gulf Stream left the coasts, north of Labrador, that would have made completely different.
Yeah, no, I think that's exactly one of the points here. And
So the word Gulf Stream should be more Gulf Stream departure.
well, so that is actually a vocabulary issue, because my advisor would argue that the circulation of the current in this region should be called the Florida current. And when it separates, that's when we call it the Gulf Stream. So that's just a tricky issue where some people want to call one thing a Gulf Stream and another a different thing a Gulf Stream.
Who's your supervisor?
So that's Luann Thompson and Kathy Kelly, who both feel that way.
But isn't the Gulf Stream separation latitude a problem that a lot of the ocean models?
It is, yeah, it's a big problem, and my master's research was actually looking at just that. And we ran the GFDL model at an 1/8 degree resolution to try and resolve eddies and see if we get a better separation. And it turned out that our separation was also really dependent on our lateral boundary conditions, because we were just looking at the North Atlantic. And it just turns out that separation is not just related to the dynamics in the upper ocean, but they're related to what's going on throughout the column. They find right now that they get the best separation not when they go to the highest resolution, but when they have kind of a mixture between a high resolution and good parameterizations of the isopyramid mixing.
I mean, one general piece of advice is that there's overall not as much work on trying to compare the situation of the North Atlantic and North Pacific storm tracks in terms of the formation mechanisms. And if you want to test your mechanism, it would be good to start looking at the Pacific as well, because there's clear differences, but also several things that are very similar between the two in terms of both the forcing and the tying stages, with one tying over Europe, the other the Aleutian Roll, and how that affects the storm track strength and direction. But and that's something I've always been curious why more people don't do, compare the two and try to understand the dynamics of the storm track formation through the comparison of the two tracks.
Yeah, I agree. One point on that, I think, is that the complication in the Pacific is that midwinter suppression. But I agree that after you leave the entrance of the storm track and start looking at what's going on throughout the middle of the ocean gyre, that the differences between the two kind of lend themselves to some interesting aspects. Great, thanks.
All right.